Evening, everybody. Tonight I have kind of an odd looking function of n based on the pi product notation. This reads f of n, and we could do without the notation, I suppose, but it is a function. In a previous video I showed this is not a one-to-one function, but in any event our n determines everything here in terms of k. Now let me just show you what I mean by that. And what we're going to do is actually prove there exists a solution under these circumstances. If this constant divided by 2 minus 1 is prime, then it is a solution. Okay, so let's just take a look at why that might be true. First of all, what does a prime number mean? Okay, prime number, examples of a prime number is like 13, and it's very well known that a prime number has two divisors, namely itself and 1. Okay, so it has exactly two divisors. That's the essence of a prime number. That's the definition, okay? So we're going to show that if k over 2, and again, k is this constant that appears right here, minus 1 is prime, then it is a solution. And it's a fairly trivial solution. So by definition, 1 and k over 2 minus 1 are the only divisors, right? I mean, that's just straight from the definition. Nothing too sophisticated there. All right. And so that means d plus 1 only takes on the two values 1 plus 1, and then k over 2 minus 1 plus 1, right? I mean that's what we're doing is we're adding 1 to the individual divisors, okay, in this original expression, okay. And so what we would get right here is that if n is equal to k over 2 minus 1, and I should write down that this is equal to k. All right, then you see how this is just not much going on here. In other words, you would have this is equal to 2, right? 1 plus 1 is 2. It's equal to 2 times. Well, if you add 1 to this, right, what do you get? You just get k over 2, right? So you have k over 2. So you see, it's trivial. You know, sometimes the general proof is easier than discovering these things numerically. All right, but that does equal 2k, right? Okay, so we've shown that the integer n equals k over 2 minus 1 a prime. Again, we're just hard coding it. You know, we're saying it is a prime. And if it is a prime, it has two divisors, and when you add 1 to each of those divisors, you get a product that's equal to k. It's simple as that, okay? Now, if you want to look at a more concrete example of this, let's try maybe 228 for, let's do n equals 228. Okay, now, so we would have 228 over 2 minus 1, right? 228 over 2 minus 1. Okay, is that 114? That's equal to 113, right? And it doesn't take long to verify that 113 is a prime. Okay, this is definitely prime. All you have to do is check the divisors 2, 5, 7, I think. You don't have to check 11 because it's less than or equal to the square root of 113, which is less than 11, right? So in other words, this is prime. All right, and so this above result, I won't write it down in the name of time, but the above result would yield 2 times 114, right? Again, all you're doing is incrementing the two divisors here. That's equal, of course, to 113 times 1, right? So trivial stuff, really, but that does equal to 228. But I thought it was kind of neat because this came from a textbook problem by Charles Vanden Eynden where it was just the constant was 396 and you were supposed to find the n and that was it. But you can actually generalize it to where this object becomes a function. I don't know how interesting it would be in other realms or if it's just kind of something that I noticed. Not a big deal really, but again, it's kind of fun to see the structure going on, to think of this expression as a function of n. All right, that's all, folks.